Good evening, everyone. Welcome to the Tucson Amateur Astronomy Association first Friday of the month meeting. We're here at 6:30, the first Friday of every month, and we have people in person in the auditorium with us. We have people attending on Zoom, and we have people who are attending via Facebook. And our Facebook recording will be posted, and it will occur later on YouTube for people who want to access it there. So we're delighted to have everybody here with us. I'm May Smith. I'm the TAAA president. And we have several people who are helping us with technology tonight. We're having Jim Knoll, who is over here next to us operating the system up here. We have Terry Lappin, who is working with Facebook. And we also have Susan Knoll, who's going to be operating our camera tonight. We need to ask people who are in the room to please not have conversations anytime we're on Zoom, because the Zoom in the room does pick up the conversations, and so it will create a problem for other people. Please refrain from that. We are going to have a main presentation in a minute here, and I'd like to ask people who are on Facebook or who are attending via Zoom to make sure and enter your questions typed into the chat areas on there so that we can make sure to address everyone's questions when the speaker finishes his presentation. And then we will also take questions from people in the room. And I will need to move around and share the microphone with people in the room. So we'll have a little bit of time that will be consumed in waiting for me to get from one place to another at that point in time. We have a great presentation for you tonight. We have Carson Fuls, who I'm sure you've gotten some information about that's been sent out several times on his background. He works with the Catalina Sky Survey, and he's got some really important and very interesting things to share with us. So, Carson.
Is everybody hear me? Excellent. All right. I'm going to go ahead and jump on in. There we go. All right. Like May said, I'm Carson Fuls. I work with the Catalina Sky Survey, which is across the street at LPL. And I'm so glad to be here talking to other astronomers because I could really use your help. So this is kind of an ad to see if you can join me in my project. As you probably know, y'all might be familiar with Catalina Sky Survey. If you're not, well, what do we do? What do we do up on Mount Lemmon and Mount Bigelow? Our number one goal, our only goal, is to find near-Earth asteroids, ideally before they hit the planet. Afterwards, not our problem. But that's it. We've been running this survey for over 20 years now. And we've been doing pretty well, but the reason we've been doing pretty well is not because we have great telescopes or great facility or great support here from U of A. It's really that we have a really great team. This team, since I have joined over 8 years ago, has doubled. We're up to 16 people now, but you know, we have the nice 60-inch telescope, but this is really Catalina Sky Survey. All these people that work very hard every day and every night. Little bit about our objects of interest, near-Earth objects. Y'all probably know this, probably all old hat to y'all, but these are mostly going to be asteroids. There are a couple of near-Earth comets. Those are particularly scary, but anything that has a perihelion less than 1.3 AU we're going to consider that a near-Earth object, and that's something that we care about. We sweep up a lot of asteroids and comets, not too many centaurs and no TNOs, but we really mostly focus on near-Earth objects, and everything about our survey is optimized to find these. So far, and I just checked yesterday, we're at over 32,000 near-Earth objects in total that we found since we started looking. And at the going rate, we're adding about 3,000 new objects every single year. But we still got a long way to go. Depending on what size you're talking about, all the big ones, yeah, we've got those pretty well nailed down. The smaller ones, no, we still have a ways to go on those. Why do we care about them? Well, of course, because they can impact the Earth, and we care about the Earth because that's our home, right? But why? What can they do? I'm sure everyone here is familiar with this. What happened February 15th, 2013? That's actually my birthday. Great birthday present because it wasn't here. But yeah, over Russia, this wild and crazy thing happened. I won't play the video and scare everyone with the sonic boom, but that was in the other presentation. But this was a fairly small asteroid by our standards, about 66 feet, 20 meters. And this airburst, that means, it didn't actually come down, hit the ground, form a crater. There were some fragments that were discovered, which you could probably pick up a piece at the Gem and Mineral Show if you got the cash. But yeah, this one didn't even make it to the ground, but still 400 to 500 kiloton explosion in the atmosphere from a small rock. It did end up injuring 1,200 plus people, but thankfully no fatalities, which is about as good as you could hope for with a situation like this. But there's been others. The Tunguska event, 1908. This was a larger asteroid or comet, maybe. We don't know for sure. This was quite a much bigger explosion, 10 to 15 megatons, TNT, and flattened 2,000 square kilometers of forest. Good thing it was over the almost totally uninhabited Siberian tundra, but it didn't have to be. This, I'm sure you're also very familiar with, living in Arizona. Meteor Crater, also called Behringer Crater, get that right. This was a pretty good sized asteroid, but like I said, not that big. It happened long enough ago, though, that it might have killed some woolly mammoths and ground sloths, but that was about it. But if this happened today, this would be a big deal, right? And finally, the one that makes all the great movies that people like to watch, the impact event over the Yucatan Peninsula in Chicxulub ended the reign of the dinosaurs. It wiped out a substantial percentage of the biosphere on the planet, and it totally changed the environment. This is really what we care about. This explosion is off the charts, basically. But thankfully, that's not going to happen. How do you know, Carson? Well, we know because we found most of the objects of this size. I say most because I'm a scientist and I don't like, exact answers. There might be one that's hiding, always on the opposite side of the sun, that we just never see. We found most of them. How do we know that? Because we keep looking year after year, and we keep improving our telescopes, our cameras, and our software systems. So we're doing a better job looking, but we don't find any more. So that rate over time has not been growing, so we can say confidently, probably no extinction event objects that we haven't found yet. What have we found so far? A lot of space rocks. If you'll notice here, this is the discovery rate over time. It really kicked up around the year 2000. This coincides with the development of CCD cameras in astronomy. A really big paradigm shift in the search for near-Earth objects. In fact, Catalina Sky Survey started in the late 90s, not with CCDs, but with film, just regular film. It was a good night if they could get 12 or 13 or 14 images. But they still found some rocks, and that's how we got started. Today, you'll see all the different surveys working together. Catalina Sky Survey is here in green. We are very productive and account for almost half of all the near-Earth asteroids that are discovered in total. This one's a little bit outdated because this is only for the first of 1, 2, 3. Yeah, I need to update that one. We found some more since then. Anyways, that's why we do what we do. How do we do it? The nuts and bolts. I'm sure this is what half of y'all came for. These are our telescopes, 4 of them. We use these 2 right here. This is our 60-inch telescope at Mount Lemmon Sky Center. This is our 0.7 meter Schmidt that's at our Bigelow site, so a little further down the hill. These are our primary survey instruments. So they are what we task with finding new objects. But one reason that these survey instruments can become so productive is because we also have follow-up telescopes. Once you find an object, you have to continue following it up and making repeated observations. If we had to task our survey telescopes with that job, we wouldn't find as many objects. And in fact, that's what we used to do when I started, before we had any dedicated follow-up telescopes. Either we have the survey telescopes go after recent discoveries, or we hope and we pray that other people around the world will go after them with their telescopes. And we still do that today. But we have our 1 meter telescope, MPC code I-52, which is 100% dedicated all the time to follow up. We also have a significant amount of time on the competitively scheduled 61-inch Kuiper telescope. When we can run both of these together, especially during dark time of new moon, these telescopes can just let it rip and discover, just like we want them to. What's not shown on here is every once in a while, we also get competitively scheduled time on the Bach telescope, the 90-inch down at Kitt Peak. And we use that for more survey. That's a joint program between Catalina Sky Survey, Space Watch, another big name in asteroids, and the University of Minnesota. So we all came together to share our time using the wide field imager for the Bach telescope. That is also a very productive telescope, but we only get it maybe 3 to 6 nights a month. There's also, we've been working hard to get the 32-inch Schulman telescope, also up on Mount Lemmon, to be one of our follow-up telescopes, but I haven't quite got it there yet. Still have some bugs to work out. Survey telescope field of view. This is why we can find so many rocks. Our Schmidt telescope has a 20 square degree field of view, which if you've ever seen a monolithic 20 square degree image of the sky, it is breathtaking. It is simply breathtaking. This size field of view lets us cover the entire northern hemisphere sky in about 3.5 nights. And then we just start back over because the sky refreshes itself. Start back over again and again and again. Now, this is a smaller aperture telescope, 0.7 meters, so it can't dig down that far. Our detect 50 threshold, which is about, at what magnitude object are we only picking up half of the objects in it? About 19.5. That's not bad though. And these are all 30-second images. What I didn't put on here is that we have big, chunky 3 arc-second pixels. So we have nice square stars. Our 60-inch telescope has a much smaller field of view, but still substantial. 5 square degrees is also very nice. But we can see much deeper with this one. This is our discovery powerhouse, just because it can punch lower than the Schmidt. The Schmidt is ideally used for very fast, close approachers that are, have just gotten close to Earth, got very bright before they pass by or impact. But the 60-inch finds objects that are smaller and further away, which is great. It accounts for the majority of our discoveries. Its detect 50 threshold 21.5. And I will tell you, if it's a good clear night on Mount Lemmon with very good seeing, we can easily make plenty of discoveries at 22nd magnitude all the time. And I can't get away from the field of view without showing you our beautiful 10K by 10K CCD cameras. Thank you for these. That is a gorgeous single piece of silicone, and it's what really enables us to have the discovery rate that we have. Monolithic, so there's no gaps in it, which is great. And these come from Spectral Instruments here in Tucson. Okay, I wanted to talk about the nuts and bolts of Catalina Sky Survey before I got to how you could help out Catalina Sky Survey. So our normal every night routine is we start with our telescope and we take 4 images of the same field, right? Y'all know how we find asteroids. We look at the same field, give it some time, look at it again. Our normal cadence is 4 images. They're about 6 to 8 minutes apart. That seems to give the asteroids just enough motion that we can detect the slowest moving ones. Then we send them to our giant rack of workstations, which heat up the control room because they are pumping all night long. We do regular image calibrations, your flats, your darks, your bias. We do a star field fit to get the WCS solution for all of them. This is the secret sauce, the moving object detection, which has been refined and worked on for 20 years. Be happy to talk about that more. Once we get the moving objects, we want to ID all the known ones in the field, which sometimes can be 400, 450 asteroids that are known in the field. And any that come back as unknown are ranked. We have an algorithm that basically sorts the most probable real detection down to the least probable real detection. That's key. Our computers don't make the final decision. Humans make the final decision. We do all the processing, but we still need a human in the loop, which is by design. This is probably one of the greatest reasons that Catalina Sky Survey has had the success that we've had. We have always, since inception, had a human in the loop, actually looking at the images. Other surveys that started as, maybe they were a different type of survey and they ran out of funding and they switched over to NearEarth Objects, did not have it built into their pipeline to have someone actually look at the images. Happens. But we will always have a human look through our candidate detections. They're going to blink them like you do, and they are very good at identifying real versus false detections. This is Greg Leonard, one of our full-time observers. That's his job. For 12 nights every lunar month, he's up at the telescope making these decisions. It also allows us to submit any real objects that we find to the Minor Planet Center right then. We don't have to wait for the next day. The total time between the last photon hitting our camera and us submitting an object to the Minor Planet Center is about 10 minutes. Well, thank you. But it makes a huge difference. If we waited till the next day, those objects, the uncertainty has grown too much. It is impossible to follow them up. We have our follow-up telescope right next door to this one. So we see that there was one submitted. We are ready to follow it up. The weather's the same at both sites. So there we go. That's how we track all our new objects and the ones from the previous night and the night before that. So I wanted to first show you what you would see if you were an observer with Catalina Sky Survey and you wanted to discover some asteroids. I'm going to switch to a different one of these and show you our software just real quick. This is it, all custom built in-house. This is our full frame 5 square degree image from G96. This one has already been validated, but what you would do is we are going to give you, the observer, 22 or so candidate detections. The computer has gone through, identified these are potential moving objects, and they have characteristics that are consistent with real moving objects, more so than the other hundreds that it identified. So your job is to go through and actually look at them. Say that one, no, I don't think that one's real. That one, no, that's an edge artifact. Y'all are used to seeing these. Oh, there's a real one. Nice moving object. We do this all night long. That's it. You're going, there is no lunch break. There is no bathroom break. We are taking images the entire night until we find something interesting. There it is. I don't think that's a NEO. I think that's a comet. Got a little tail going out. Comets are always exciting. We're not in the comet finding business, but we definitely have a little competition going. But so our software shows you all these detections, and you have to do 22 during the night. Got it? Go back to the talk. All right, but there's a problem, and this is where hopefully y'all come in. Humans are great at making that distinction between false detections and real detections. But our observers will look at 200 fields in a single night, on a nice long dark night. The night ends and we can't work 24/7. So we have to pare it down. Our observers will only look at about the top 22 candidates that our software has identified. And we've tuned our detection software and our ranking system so that about 98% efficiency for those top 22 objects, which is pretty good, right? But it's not perfect. There's still a lot of undiscovered objects in each and every one of these fields. We just don't have time to look. And we don't want to automatically submit them, especially NEOs, because if we blindly submit near-Earth objects, then other people are going to spend telescope time on them. And we cannot do that. We need someone to look at them, a human. So my solution to this is called the Daily Minor Planet. It is a website. It's based on a platform called the Zooniverse, which makes it easy to set up projects to have volunteer citizen scientists look through data of all different kinds. Now, Zooniverse sounds like universe because they started with astronomy data, the Galaxy Zoo, y'all might have heard of, classifying different galaxy types. That was hugely successful, but they have broadened out to the point that now they have not just astronomy, but looking at trail cams that biologists have put in remote habitats and letting them know which animals pass through. Even translating or transcribing old whaling journals from the 1800s to get that information so that we can see what the weather was like back then, because captains recorded that. And that's a nice data source. So it has grown over the years, but the Daily Minor Planet is our little pocket on the Zooniverse. So Daily Minor Planet, it actually launched not too long ago, May 16th, almost just in time for the monsoon. So the reason I called it the Daily Minor Planet is because there are daily uploads of new data. Many Zooniverse projects get started with a specific task in mind and a specific data set that they need volunteers to go through. Once that data has been gone through, well, the project's over. Thank you for your help. We'll let you be a co-author, whatever. But I wanted to have something that's continuous, because if it's continuous, then people will keep coming back and they will keep building up their skills, because it does take a certain training of your eye to be able to detect these objects in an image. And why train people and give them a lot of that task just to end it? So every day, once we close the telescope, we start transferring our image data from the mountain down to campus. It takes a while, it's a lot of images. But as soon as it's done, our pipeline starts uploading the candidates that were not reviewed to the Zooniverse every single day. Okay, but not right now because it's monsoon, right? But we should be starting back next week. So far, over 3,200 different people have been on there and looked at these images, and every single one helped, right? Already, there's been hundreds of these volunteers that were included as measures when we submitted the astrometry for these objects to the Minor Planet Center. We want to give credit where it's due, and people are actually looking at the data, identifying moving objects. They need to be recognized for that. So far, we have submitted 427. It changes every day. 427 unreported main belt objects. And I didn't say new discoveries, because a decent number of these are already known objects. Our software just missed them. But very many of them were marginal detections at very dim magnitudes. So they are likely new discoveries of main belt objects, which is kind of hard to do now in the age of surveys, right? And 19 NEOs, just since May. So you've seen the data flow for normal Catalina Sky Survey operations. I want to give you an idea of the data flow for the Daily Minor Planet. It is much simpler. So every day, we take the images that came down from the mountain with the candidate detections, the ones that we identified during the night and the ones that were never reviewed, and we upload some of those to the Zooniverse. So our observers will look at the top 22 or so. I'm going to look at the next 18 unknown objects for every field. I'm also going to include some known identified objects, some known identified asteroids for that field, so that people don't get bored saying no, 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 no. But also I'm going to include a small number of known false detections. These are the ones that the observers actually looked at and said, no, that's not real. But there's a reason, other than people not falling asleep on the no key. I ask volunteers a simple question. I present them the blinking images and I ask, is this a real object or is it not? That's it. They don't have to, point to it or draw a circle around it all. It's just a yes or no question. Later in the day, I download the results from the project and I use their responses to the known real objects and the known false detections to compute a confidence interval, so that I can say, well, this person is very selective in saying yes to objects, and they have very good accuracy on the known and very good accuracy on the false. If they say yes, there's a high probability that this object is indeed real. Now, I had to do that because people are very clever, and people also want to discover new worlds. I don't blame them. That's what I do for a living. But they figured out, well, I'll just say yes to everything. And that way I'll be included no matter what. No. I had to find a way to filter that out. I don't think people are being nefarious. I think some people just really, really want there to be an object there, even if it's just noise. And some people will classify just as many subjects as our observers at the telescope. every day. So this is pretty much their job now. Finally, after I have downloaded the results, looked through them, computed the confidence intervals, there's going to be some subjects that rise to the top, and these need review just to make sure. Now, for the main belt objects, most people are very good at identifying those. They have fairly slow motion, a good uniform appearance, and we just submit those automatically to the Minor Planet Center. That's where the 427 main belt candidates came from. But for near-Earth objects, Catalina Sky Survey does not submit false detections. So we review these one last time just to check, right? And sometimes it's not even that they were wrong. Sometimes our software incorrectly measured an object, which we need to fix and make sure we submit the correct astrometry for it. This is our chance to do that. Just went back here. So I wanted to show y'all some of the objects that the Daily Minor Planet has identified, the nice ones. This is a NEO. It has a streaked appearance going through here, probably going, this one I think was on the order of 10 degrees per day, so it's booking it. But this was missed in our software. It was never presented for validation. So that was a near-Earth object that we just would have never seen. It would have been lost in the data. And you'll see there's asteroids all through our images, everywhere. That's one. There's plenty of others. Another nice streaked one. Very close approacher. This one is really nice because if you'll notice, it's streaked kind of PA 180 almost, but its motion is this way. This one is actually curving slightly. That means it is exceptionally close to the Earth. Here's another one. I mean, that would be hard, even if I looked at these all day, which I do, to say for sure. I can see why it got a low score in the software because it almost disappears here. And the detection changes its appearance throughout. This one is probably a monolithic body that is tumbling. But that's tricky for software to pick that out. But not for humans, because they did. Here's another one, tricky because that first detection is interacting with a background star. Right there. And look at the stars changing shape so much. That must have been a windy night. Another one, getting close to a bright background star and interacting with another one down here. That was a tricky one. But like I said, the people on the Zooniverse picked this out. The reason that the Daily Minor Planet works is because a great community has grown up around it. Now, a lot of people saw the project and they were very nervous because it has planetary defense implications. They're like, I want to do this, but what if I get one wrong? Well, no object is, dismissed or elevated just because of one person's decision about it. We're all working together. About a dozen people will look at an image, maybe less, maybe a little bit more, but it takes about a dozen or 10 or so before a consensus is reached. So you're never in it by yourself. You're not the sole responsible person. You're part of a larger community that's trying to make a decision. Of those 3,200 volunteers, I would not be able to make it work without some of the volunteer moderators. Now, these were people who came to the project who I have never personally met, but who were very active. They were very helpful responding to a lot of the comments that pop up. Each individual subject can have a comment page for it where people say, hey, I'm not sure about this one. What does everyone else think? Or, hey, there's something weird about this one. Maybe someone should take a look. That is invaluable. But these four people came from the community, and they are moderators that help with the deluge of comments, because I usually get about 100 comments every day to sort through. And that's a lot. So they take a lot of the load off where I can get some other work done. There's also two of the people at CSS helped me develop this project. That would be, these are their usernames, but that's Josh Hogan and Casper Witcheros. And that's me. I didn't come up with a very creative username. So far, there's been about 5,000 posts to the community message boards there. And that's a lot to go through, but it's been a very productive discussion about stuff. People there have ideas for ways to improve the project. Some people there who are, hopefully like y'all, also astronomers, will look at an image, see a beautiful section of a spiral galaxy. They have the tools and the know-how to go and find, where is this in the sky? What galaxy is that? And they'll post it in the comments for everyone else to see, which is great. That keeps people engaged. It keeps them coming back. And that's what we need. We need good retention and experts to review these images. This is just a snapshot of the discussion boards. You see all these tags that people have came up with, all these discussions that people are having. Someone saw a weird artifact, thought it was cool. Someone needed help with this, is this real NEO or not? Ideas about the project. We just started pop-ups for some of the known objects. If it's very tricky and people get it right, I have a pop-up that says, yeah, you're right. That was a known object. It's this one. For false detections, I have both where it pops up. If someone says no, they're like, you're right, that's not a real detection. If they say yes, I'm like, try a little harder. That one actually wasn't real. If that ever messes up, I get a bunch of comments. So I've talked about it a lot. Hopefully I've explained why I could use all of y'all's help. I think it's time to show you the project. So this is it. Like I said, it's run on the Zooniverse platform. So it comes as a website, but you can access this website on your computer, on your laptop, on your tablet. You can definitely do it on your phone. I've done that as well. Zooniverse does have an app, but some of the features of this project make it incompatible with the app, and the app is terrible anyway. Just skip it. Just use your web browser. But if you want to get started, right here. Now, I encourage people to set up an account and to also, very important, fill out this form. I keep this banner up there because this is where people get cited as measures, and I need your proper MPC format name. But this is it. It's going to give you a blinking image and ask the question, is it real or is it not? No, that one's not real. So you can just say done, go to the next one. If you want to talk about it, this takes you to the comment page. Now, the first time you come here as a new user, it's going to go through a short tutorial that's going to give you some examples of what real detections look like and what false detections look like, and what we need and what we expect from the volunteers. It is like 6 or 7 slides. You can get through it in probably 2 minutes before you get right into the data and start classifying. I think that's another edge artifact. Those are some diffraction spikes from stars that confuse the pipeline. Ooh, that one's tricky. I don't know. This is why we need humans. A computer got it to that point, right? But that's a hard decision. What do y'all think? Yes? All right. It was an unknown one. If it was known, it'd probably pop up and say, yeah, you got that right. Anyways, this is the project. This is why I was so happy to come here and show it to y'all, because I think people who are used to looking at astronomical images are the best to figure this out. They have some experience. They know that this long streak here is probably not an airplane coming through the image. That's a satellite. The sky is rotten with them now, as y'all know. All right. We could do this all night, literally. It is this one. Okay. So I'm just about finished with my pitch. I really hope that y'all come and join me at the Daily Minor Planet, that you give it a shot, that you see what you think, that you get into the comments and help people who have never looked at an image of the sky before and give them some insight and some of your knowledge. That would be hugely beneficial to the project. That's it. I need your help. We need your help at Catalina Sky Survey. If you want to, go to zooniverse.org and search for the Daily Minor Planet. I'd give you the direct web address, but it's really long, which is annoying. This is the best way to find it. Search Zooniverse and then search the Daily Minor Planet. Maybe check out some of the other astronomy related or other projects on there, but not the other ones that look for asteroids. We want all your time for that. And search for the Daily Minor Planet. That's all I've got for y'all. I'm so thankful that you let me come and give you my spiel, my stick. Yeah, thank you so much.
Okay, we will start with questions in the room, and we've got a number of hands here. So everybody be patient and I will get to everyone. Okay, first question.
Carson, thank you very much. Having been on Zooniverse for 5 years, I was fortunate enough to happen across my Minor Daily Planet, I think shortly after you all started. So, and it's nice, nice to see the nuts and bolts behind it. And I certainly hope that a number of my colleagues in the club are participating. If they don't, it's kind of fun to do at times. I do have one question.
Sure.
Your funding is primarily through NASA?
Our funding is exclusively through NASA and the Planetary Defense Coordination Office.
Okay. Does it require you to take little trips to DC and explain to the powers that be that make the sausage? Because I know that, asteroid detection has been in the news. It's, for lack of a better term, a popular topic over the past couple of decades.
Right. We don't usually have to go to DC, but we submit a yearly report to the funding office, that we get all our funding from and say, this is what we're doing. This is what we're doing this year. Our funding is actually on a 3-year grant. So every 3 years, we have to write a new grant, and hopefully we get to continue doing what we're doing. Now that has not been an issue for a while, because as you see, I think we're doing a good job. But yeah, every 3 years our funding's up and we have to reapply. But this was actually part of our previous and our most recent funding proposal, that we would roll out a citizen scientist initiative to find more near-Earth asteroids. It engages people with planetary defense in a way that I don't think has been done before. And also it spreads knowledge of astronomy, and it makes NASA look good. And anytime we can make NASA look good.
And just finally, is it fair to say you're getting adequate support?
Yes.
Good.
Our funding is adequate.
Yeah, I noticed you showed the same speed when you had an asteroid going across the screen there.
Mm-hmm.
Is it possible as an observer that you can slow it down?
So the examples I showed were just GIFs. So they're a set speed, but on the project, yes, you can select the speed.
Good.
And if you don't want them to blink at all, if you just want to look at the individual frames, you can also do that. You can show them all at once. That was actually part of the development of this project. The Zooniverse really went above and beyond and built some extra functionality into their user interface to allow just like that variable speed. You can invert the image, which really helps sometimes, and you can pause it to be static.
Thank you.
Yep.
Yeah, that was wow.
Oh,
I've
thank
been
you.
very impressed by the Catalina for years now. The things you guys are coming up with are great. And this whole new idea of the citizen science being a way of pushing down to deeper and deeper magnitudes and catching more of them. Wonderful idea.
Oh, thank you.
Anyway, 2 questions.
Sure.
Last one's pretty short. The first one is, okay, you've convinced me that you've caught most of the possible Earth impactors, at least the big ones.
Mhm.
And fair enough. Okay. But you studiously ignored the comet threat because we don't get notice of them in advance. We might get a month or a week notice of an incoming comet. And comets can be very big enough to, well, cause a lot of damage. So what is the relative rate of comet civilization destroyers versus, or some, I'm not sure how to phrase this. What is the rate of comet impacts versus asteroid impacts of a given size?
Because of the time domain of comet orbits, that's hard to put numbers to. All we can say is that, you know, we've been observing the skies for a number of centuries, and very close comets are much rarer than very close approaches by asteroids. Yes, comets are terrifying. They come at wild inclinations. They can come from below, they can come backwards. Their kinetic energy, because of their orbit, is much higher than asteroids. And comets are usually fairly dim until they reach the waterline and start to sublimate. And then we can see them. Then, you know, that's when they turn on. Thankfully, comets that come very close to Earth are rare, as far as we know.
Okay, that calms me a bit. My second question. Okay, so you work for the Daily Planet. Dark, short hair, nice. You've grown a beard now. Could you take off your glasses for us to see you?
Yeah. But now I can't see y'all. Okay.
Okay, thank you.
By the way, I did just Google it and it showed right up, so it's easy to find.
Beautiful.
Yeah, a couple of questions. So you said you basically observe when it's darkest, and it seems like there's almost half the month that you don't observe or you can't see anything. And I mean, there's got to be still stuff out there. How do you try to even find it?
No, we observe all except for 1 or 2, maybe 3 nights around new moon.
Okay.
Now, right now we paused because of the monsoon, which is about 6 months of it raining and being cloudy. And the big threat to us for monsoon is lightning. Our instruments are up on top of Mount Lemmon. They are a lightning rod. If there's lightning in the area, we go through and actually pull the plugs, because our beautiful spectral instruments 10K by 10K CCD camera would be almost impossible to replace. So that's why we're paused right now. But yeah, during normal rest of the year, 2 to 3 nights, we take a break around full moon. The skies are just washed out. For our telescopes, we've tried observing at that time. We just, it's not productive. And our staff needs some time, you know, a break, because if you are observing for us, you're scheduled for 3 nights in a row, you're going to live at the observatory. So it's a hard career. What could we do better? What could we do to find more of these objects? The Northern Hemisphere is saturated with surveys. We are here. The other major survey is Pan-STARRS in Hawaii, Northern Hemisphere, you know, a little a little bit further south, but still northern hemisphere. Atlas, another smaller survey, does have some southern hemisphere sites that just came online, but they're also in Hawaii. But those are small telescopes, so that would be similar in capabilities to our Schmidt. So they're not going to find 22nd magnitude objects at all. Impossible. What do we need? We need more resources, more survey resources dedicated to NEO discovery in the southern hemisphere. That's what we need. Fortunately, we are working with a group from the Korean Space Agency to build basically a clone of our G96 telescope to do just that, a dedicated NEO telescope, which will be in Chile. But yeah, that's where we need to go to up our ability to find these objects. I would put a G96 on every continent and just run it all the time.
Okay, the other quick question, not a CSS question, but I guess there was something in the internet news earlier today about some amateur astronomers caught something that hit Jupiter.
Oh, wow.
So I was just kind of wondering if you knew about it, any speculation of what it was? 'Cause it
No,
looked like-
that is fantastic. I haven't heard about that. I will say, because this is the Amateur Astronomy Association. In the last few years, I have seen a huge uptick, not just in follow-up from amateurs, which we always need, but from discoveries from amateurs because of new software that has come online called Tycho Tracker. You basically trade doing a wide field of view for taking several exposures of the same region of sky with your 12-inch telescope. Take 12 exposures. The software is very CPU intensive, but it will blindly stack them along every possible vector to try to build up enough signal to detect an asteroid, and it works. So if I had my own telescope, which I don't have plenty of problems with telescopes, I would be using that because there have been quite a few discoveries recently of near-Earth objects by amateurs with smaller scopes. And they are leveraging advanced computing technology to do it. So computers are way cheaper than bigger aperture, right? Tycho Tracker, TYCO.
Earlier in your presentation, right at the beginning, I think you mentioned you estimated there might be 10,000 objects yet to be discovered. What criteria are you using to make that determination?
Oh, not solely 10,000, tens of thousands, many multiples of 10,000. We make that estimate by, it's a little bit circular. The surveys build up an inventory of known asteroids. Then people take this inventory and turn it into a population model. We can do that because we look at the, not just the total number of discoveries, but the rate over time. So looking at that rate, we see that it's not static, it's actually the rate is increasing. So we're finding more and more every year. Using that, looking at the trajectory, we can estimate a population, and they're just estimates. But the population models show for asteroids in near-Earth space that there's about 1,000 kilometer size objects, but then it goes up orders of magnitude as you go down orders of magnitude in size. So for 100 meter objects, another order of magnitude, so there's 10,000. For 10 meter objects, there's 100,000 like that. That's basically the population model as we know it now. We'll refine it as we keep finding more asteroids. We can narrow that down, but it's just an estimate based on rates. That's as good as we got right now.
Sorry, I accidentally hit the microphone there and it certainly doesn't like that behavior.
Two questions. One that I'm also stealing from Chris Fold on chat. Has machine learning helped improve your pre-processing pipeline for the initial passive detections that you pass on to your observers?
Not machine learning per se. Our pipeline has not been through a machine learning training regime, because our pipeline was developed so that we understand all the inputs that go into it and can modify them. If we just took the data, we could take image data or source data, whichever you prefer, and feed that through an algorithm. In fact, other groups besides CSS have done this. They come up with a pipeline that works, but the efficiency is not any better than the one we have. And they can't tell us how to improve it because they don't know what it's based on. Right? So no specific machine learning. I mean, we tune to the parameters that we know. We have a target. We want to try to find large, distant asteroids. So if we have to sacrifice missing some of the very small, close approachers, well, our directive is to find the big ones. So we will do that. But we can say that we did that because that's something we know and can tune to. Machine learning, don't know.
And the second question is, how much data gets generated per night on the typical average?
Oh, I think between both survey telescopes, the Schmidt, I think G96 generates 1.5 terabytes a night, and the Schmidt generates 1. Yeah, and we pump that down the mountain every night. Yeah, data storage and archiving is a big part of our operation. Not a fun one, but it is very critical.
Okay, I think that does the questions in the room. If I've missed anyone, okay.
One more.
Yep, did miss someone, so we'll get that.
I was just a latecomer. Just a question for those citizen scientists who participate. Are there any like time restrictions and for them to be able to review the images and to respond?
No, not at all. So during normal survey operations, we upload data, not exactly in the morning, about lunchtime, Tucson local time. That's given it a chance to all get down the mountain. If you want to hop on right after that, feel free, you'll get the freshest data. We keep 5 of the previous night's worth of data up. So every day we will add a new data set, remove the oldest data set. So we have a 5-night window going at all times. Now, if a promising candidate rises to the top, of course, we'll retire that, but that just gives people a chance to review the other detections that haven't had enough people see them. So no, there's no specific time requirements for you or anyone else. In fact, one benefit of this project being global is that people from all around the world get to it and they're working on it all the time, which is great.
Thank you.
Mm-hmm.
Okay, thanks. I think we have some questions now on Zoom. As soon as I get the microphone to the front of the room, we can address those.
All right, let's see. We'll start from Jeff Tversky. He asked, can you talk about Oumuamua, what it is and why it wasn't picked upon before it passed Earth?
Quick story. I was actually at the Kuiper 61-inch, and some of y'all may be familiar with it. It's on the Minor Planet mailing list. It's just a listserv for people who really care about minor planets. And I'm at the Kuiper doing follow-up observations. I'm not looking for new objects, but I see an email that pops up from Bill Gray, Project Pluto, who lives up in Maine. He's an orbital dynamicist, and He works with Catalina Sky Survey a lot, so I know him fairly well. And he comes on and says, hey, there's this object on the NearEarth Object confirmation page. And I have tried every which way I know to fit its orbit. But the only thing for me that works is a very hyperbolic orbit. And I think that this object actually is an interstellar object, which was mind-blowing. So of course I steer my telescope to get follow-up of. That was probably one of the most exciting nights I've ever had at a telescope. You know, first time ever came through our solar system. What is Oumuamua? You know as much as I do about it. We didn't follow it up much past determining it was not a threat to Earth, right? So that's where my concern with it ended. But it appears to be very elongated object, very red, as you would expect for something that's been in interstellar space for a long time. It was first designated as a comet because the Minor Planet Center has really squishy rules about when things are comets and when are asteroids. It had a comet-like orbit initially, but it never showed any activity that we could see. So it's just a regular space rock just visiting.
All right, this one I think you already answered. Can you slow down the blink rate? And you said yes, you can. Next question from, let's see, is light pollution from Tucson having any impact on your limiting magnitude?
Short answer is yeah, of course it is. But coming from other places, I'm not from Tucson originally. Tucson is profoundly dark at night, and has done an admirable job of preserving the night sky here, which I'm sure is near and dear to everyone here. I can say from the top of Mount Lemmon, the light pollution from Tucson is matched by the light pollution from Phoenix. So Tucson to the south appears just about as bright as Phoenix, way over there. So things could always be better, but I'm thankful for what we have, and I know people are going to continue pushing to preserve our collective night sky here. So.
All right, Thomas asks, how many minutes between images? How many images taken of the same area? How much of the sky can you sample each night?
Okay. We always do 4 exposures of the same field. That's a good, in case there's star interference for one of those on a moving object, we have 3 others. We can still make a line. So we do 4 images. The separation between them is about 6 to 8 minutes, which gives us enough motion. NearEarth objects are pretty fast. So all we need is about 6 minutes. Coincidentally, our images are completely blind to trans-Neptunian objects because our pixels are so big. They don't move far enough in 25 or 30 minutes to even change pixels, so completely invisible. We average about 200 fields per night, and each field is 4 images. So that's 2, 3, 4 math. 800 images a night. Sky coverage for our Schmidt telescope is about 1/3 of the night sky. Sky coverage for our 60-inch telescope is, what is it? We can cover about I'd say 1/20th of the sky every night with it. And we usually just work down deck bands just for consistency. But it's rare that we get 29.5 uninterrupted clear nights. Just doesn't happen that often.
Thomas also asks, is there enough information to determine its orbit, or do you need multiple sightings? How do you track this?
Just from our 4 positions, we have a very, very rough idea of its orbit. So we really need prompt follow-up. It is critical that we get prompt follow-up. That's why not only are we one of the leaders in survey, we are one of the leaders in follow-up because we had to take care of our discoveries. But we really need as much follow-up help as we can get. If any of y'all do asteroid follow-up, come talk to me after the meeting. Catalina Sky Survey has some more tools that we're trying to roll out to help with prioritizing targets for asteroid follow-up. But yes, prompt follow-up, critical.
Okay, I'm going to go back to one. I think you already answered this, but just in case it's a little bit different. This is from Chris Fuls. Good application for all our data formatted for integration into machine learning. I know you talked a little bit about machine learning, but I don't know if you addressed that.
Yeah, we have consciously avoided producing a new moving object detection pipeline based solely on machine learning. The Zooniverse is often used for machine learning training applications. So you need a good training set to start a machine learning routine. But that for our data, that would be slicing it up and asking people, is this a streak? Is this a asteroid detection? Is it a star diffraction? Or is it some flat field noise? And that's not fun. That's not making big discoveries. So yeah, we have not got there yet.
Okay, and the last question is from Wade. How do amateur observers report possible NEOs?
For our project, all we need you to do is say yes or no. Because since these are taken with our 60-inch telescope, the reporting of it is tied to our MPC code. And the MPC will not accept astrometry from that MPC code from other people. That's just a way to keep everything straight. If you have your own astrometry, you need a site code from the Minor Planet Center, and you need to report it to them, either via curl or via their web form, or there's a couple of other methods.
Okay, from Facebook, we do have some tonight. From Tom, he's asking, how can you tell when it is tumbling?
When it's tumbling.
When it's tumbling?
So it's hard to tell with nice round detections because you'd have to look for a change in magnitude, and usually that's so very slight that you just can't tell with your naked eye. And our telescopes are not they are not optimized for photometry. That's not what we're going for with our big giant pixels. I can tell some of them are tumbling because they're streaked, and the brightness of that streak will change. So, I mean, these are very, very close objects. Imagine something the size of a, not like an 18-wheeler, but a little bit shorter than that. Like a delivery truck is tumbling, so you get the front side, then you get the profile, and then you get the back side. That's what you're seeing with a streaked object when it's getting a little brighter and a little dimmer inside that one single streak. So that's how I can tell some of them are tumbling.
And then the last one is from Lamis Mita. She says, this is awesome.
Oh,
and
thank
can you
you.
do it from outside Arizona? I think you already answered that. It's worldwide.
Absolutely. Anywhere you have an internet connection. And like I said, it even works on your phone. So the times when you're just doom scrolling through all the bad news, go find some asteroids instead. Right.
One more on Zoom from Mike asks, what is your relationship with Spacewatch?
Spacewatch and us are both at the Lunar and Planetary Lab, and we do collaborate for NEO survey on the Bach telescope, the 90-inch Bach at Kitt Peak. They're a great team. They primarily do follow-up these days, and we depend on them for our huge follow-up needs because of all our discoveries, and they are exceptional at it.
Great. Carson, thank you so much for this presentation. You really, I think, inspired a number of people here to become more involved in this effort. And we really appreciate that. And Carson has, I think he's going to hang around for, we're going to have some soft drinks after the meeting in the lobby. And Carson has agreed that he'd like to hang around and be able to talk to people here more, at the refreshment time. So
Yeah,
thank you so
absolutely.
much.
Well,
And we, one requirement that we have for people that present us to us that have ongoing projects is that now that you presented to us, you're required to come back and report later on some other results or whatever new you would like to add.
Oh, absolutely. I will take you up on that anytime. Thank you so much for hearing me out. This is the perfect crowd to get involved in this because we really need some help from experts. So thank you so much for having me.
Thank you. Okay. Okay, so now we're going to do a little switch off with computer things here. And we have a presentation from Ed Foley. Yes, I'm sorry, we're going to stop Facebook at this point. Forgot to announce that we appreciate all the Facebook people coming and being with us. And we will be here the first Friday of every month at 6:30. So we hope that you will rejoin us again. And we hope that you will go to our website at TucsonAstronomy.org and look us up and read some of the information that you have there and figure out how we might interact with you more and create some more positive learning experiences and sharing experiences with you. So thanks for coming, Facebook people, and we hope to see you again.